That says how much time I actually work, and it was stopped, so I didn't notice that there was not much over the day. So, unless you really want, I think it's better to go up to the end of the class right now. Tomorrow I'll be more careful about that. Okay. I want to say a couple of things about adequacy criteria, and then move to a more detailed topic, and we'll discuss which one. Adequacy criteria. Do you know what an adequacy criteria is? Okay, let me just tell a couple of things here. Okay, so now we're going back to testing. Okay, so we see the big picture in a different dimension, different properties, testing. Now, before discussing different approaches to testing, how many approaches do you know to testing? Do you know structural testing, statement coverage, range coverage? Most of you? Some of you? Yeah. Do you know functional testing? Which criteria do you know from functional testing? Okay, cover the requirements, yes, but do you know any way to do that systematically? You know category partition testing? You know category partition? You know catalog-based testing? Binary varialized, okay. Okay, I see some, you know something. But probably not all of you at the same level. I guess the group is not homogeneous, but I try to get to the point where we all understand it. Okay, one problem is, let's say, meta problem is not what criteria, how to define a criterion, but what is a criterion and how I actually compare criteria. So I'd like to get to this point, which is interesting, but not very exciting, which is an adequacy criterion is a way of measuring the effectiveness of testing. Okay, so the question is, I really want to be able to say, is this testing adequate or not? Which means, can I say something about if a test passes or if the system passes a test which is adequate, then the system actually is adequate, hopefully correct. Okay, that's actually the real goal. And as I hope now I convinced you before, it's impossible. So we can't really connect the correctness of the software to the adequacy of the test. I'll ask in a few cases actually. Can you tell me a test which a criterion that has this property? So, that's an interesting question. Let's see if you follow me so far. So, you have a software, okay? You have a test. A test is a set of inputs under which you want to run the software and see whether the software fails or not, okay? Now, another adequacy criterion is something that characterizes the test. So, for example, I understand that you all know statement testing, which means execute each possible statement at least once, okay? Okay, and so now the statement here says, I cannot have an adequacy criterion with this characteristic which says if the system passes the test, then it is correct. Alright? So you all know that even if I do have 100% statement coverage, the system may not be correct. Okay? So that is definitely the case where it's not adequate. Right? Now the question is, do you know any criterion which at this point, of course, may be infeasible in terms of applicability or inapplicable. Do you know any criterion that would actually satisfy this property? Which is the same way of asking, how do I prove the software is correct by testing? Exhaustive testing, exactly. So
measure and test coverage.
Pardon?
Measure and test coverage.
No, measure and test coverage is not enough because any coverage does.
It's not enough, but it's one more driver.
Oh yes, but the question was a bit different in this case. And the other is exactly correct. It's exhaustive testing. There is one case where I can assure that if the system passes a test that satisfies the criterion, then the system is correct, which is requiring each input to be executed at least once. okay, which is exhaustive testing, which is, of course, impractical, but that's okay. So, what we do have is, instead of actually looking at adequacy criteria in the way they should be, we call adequacy criteria the ones that actually are inadequacy criteria. So, what we do usually is, instead of looking for impractical adequacy criteria, we look for practical inadequacy criteria. So, what I think is really important is, whenever we talk about statement coverage, branch coverage, data flow coverage, whenever we talk about category partition, catalog testing, requirements coverage, what you're doing, you are not fixing anything which is adequate. You are excluding things which are definitely inadequate. So, the criterion is a criterion of inadequacy because it doesn't say if you cover all statements, then you found all faults. No. But it says, if there is a fault in a statement, and you do not execute that fault, you definitely do not reveal that fault. So if you think about statement coverage, and I hope you understand what it is, statement coverage. Statement coverage means you have your program, and let's actually draw the program. As a control flow diagram. Okay, a bad one. Okay. Statement coverage means execute at least once all possible statements in your code. Now, this does not guarantee anything about faults. But if you do not satisfy the criteria, let's say you have a fault in this statement and you do not execute that statement, then you definitely don't find a failure. So in this way, it is more correct to say inadequacy criteria, even if you don't find this word anywhere except our book. Okay, so people like to talk about adequacy, but it's actually talking about inadequacy. Anytime you say this is the criterion, remember what it says. If you go outside this, you lose something. You are inside this, you can't say anything. Okay, that's the point. Okay. Comparing criteria. Okay. Can anyone tell me whether statement is better than branch coverage or source? So,
am I right in thinking that branch coverage includes statement coverage?
Oh, that's actually an interesting. So his statement is branch coverage includes statement coverage. Correct? Okay, let's see if you understand what we say. We are saying, okay, and you forgive me, I don't project Java code, but just fake control flow diagram. Okay, statement coverage means cover all statements, which means cover all possible nodes in your graph, control flow graph. Correct? Branch coverage means cover all branches. Okay. Okay. Now the question is, would you compare the two criteria? And if so,
it's not the same.
It's not the same. No, there are two different criteria.
And they are not included in each other, in my opinion.
They're not included. Okay, so let's start from this.
Because the behavior of program depends on concrete flow. I mean, from as you pictured. The program may go through one flow and the result will be X, and may go for another flow and the result will be Y, while it will go through the same statement.
Okay, so we have branch statement, right? And there is two different schools here. One is the left school, which is branch is better than statement. Another one, which is on the right, is not comparable. Correct? Okay. Now let's see who's right. Okay. Any other opinion?
Actually, when you cover all ranges, you cover all statements.
Okay.
No matter what the result is.
Right. So he's the theoretician. So he knows. Okay. So there is one point which is, come on, this is a graph. You know, we've been studying graph forever. I'm sure you did actually. Everybody did, you know, including myself. And everybody knows that if I traverse all arches, all edges in the graph, I do traverse all nodes and not the contrary. Okay? So there is one obvious statement that says, you know, from our graph theory courses, which I'm sure you actually have suffered for a while, you know that if you traverse all the branches, you pass through all nodes. You also know that it's not through the contrary, so if you go to, you can go through all nodes without traversing all nodes.
But that doesn't matter.
Okay, so this reason supports inclusion. Okay, so they say, you know, come on, this is true, you know, branch is better than statement. Now, is this consistent? No, because, and there is another point which is now, so it is true that if a test case T satisfies branch, then it satisfies also statement. Okay? No doubt. Okay. It is also true that if a test T bar satisfies statement, there is no guarantee. It's not false, but there is no guarantee that it satisfies branch. So this relation holds in this respect. Okay? And this is called actually subsume. You know this name? Not that. Okay. So, subsume relation means the criterion 1 subsumes the criterion 2, branch subsume statement, if and only if every test case that satisfies the criterion 1 satisfies also the criterion 2. Okay? And this is true branch subsume statement. Statement does not subsume branch. I think it's also true, I guess, that you understand that this is not a total order relation, but a partial order. So you can compare some criteria, and you cannot compare other criteria. So you actually get to that. Okay, now this is yes.
According to this graph, you can go through the states through different paths. Is it not criteria, or does it include it in branch criteria? So each state, from state A to state B, you can move through different paths. So the program state is changed not in the same way.
Oh yes. So you're suggesting, as you understand, you're suggesting, come on, there is statement coverage, there is branch coverage, there is also path coverage, which is another one. And let's see, does path coverage subsume branch coverage? Yes. Okay. Now, let's go back to his point, because his point is really good and actually connects everything together, which is, come on, this is a stupid relation, or it's a useless relation, because he says, no, you know, there is another point here, which is, I can get a test case and see whether it is right or not. He says, let's get a test case that covers all branches here, and one test suite that covers all statements here. Okay? Which one discovers more faults? Okay, so that's exactly this point. You know, he says, you know, correct? He's saying, yeah, we can compare criteria, but still we cannot get the real comparison. So this is actually, by the way, an interesting open research issue, which may stay open forever. I don't know. Which is, yes, we do want to compare criteria. Okay, there's no doubt, because people ask, you know, people in community practical people, you know, in practice saying, what criteria should I adopt here? Should I cover branches, statements, paths? Okay, no. That path is not a question because paths are infinite. So it's a nice criterion, but it's a sort of top level. Okay? And so people do actually care about comparing criteria. What's happening is that right now, the one that we can do, the most common way of comparing them is this subsume relation, which is a nice little piece of theory with very little implications. And you're right when you say we really would like to do something better, which is to compare criteria according to the number of faults found rather than to the to the number of test cases selected. And that's actually a good point. People can do something actually, but there is not much to be done so far, at least not publicly available, which is you can compare criteria according to empirical data. So one thing that people will do is, I did actually experience so far that by using statement coverage, I did enough, and I didn't get much more with range coverage. Okay? And so you can actually empirically get some evidence, and whether you can compare them by the way of this or other criteria, by the number of faults they can reveal, it's an open resource question. Yes?
This depends on particular test cases that you take. I can invent maybe some real statement coverage tests, which does not satisfy range coverage.
Yes.
And but this is kind of art.
Oh no, it's not kind of art. Okay. Let's see. Let's skip a couple of things and go to this point because I think is okay. Well. Yeah, well, I have the slides on subsumer. I told you. Let me actually go to this one. No, it's not a kind of art. It's more like. Let me go to this one and then come back to this point. How to use criteria and why it's not well. Okay, let's say you are right in the sense that proving this is a tricky thing. So I'm sure, you know. So when you say it's a kind of art in the sense that you're saying, can I find a criteria that satisfies the statement and not range? Yes, it's a tricky thing and you can do that or not. Actually, there is a much more deep thing, which is I can run my test cases, and that's exactly what I do here. I select test cases and I use, for example, functional test cases, and I go back to this later. I run the test cases and I measure coverage. So the real rationale between these two things is, and let me go back for a second. I get my software. I know what the software is supposed to do, which means I may have the specifications, I may not, I may have some suggestions, I may have some manuals. So when I'm saying functional testing, I'm saying I have some clue about what the software should do, all right? And in this framework, what I can do is I have program specifications. I execute what do I start from?
Start from the specification. I have to assume something, assert something, run the program to check that output. I mean, the specification.
Okay. Everybody agrees? So let's make the intermediate step. Program specifications. You have to derive test cases. So your goal now is not to develop the software, not to define the specification. It's just try to check whether the program matches the specification. And you decided that you do it by testing. Okay? Now, program specifications represent the two sources of information you can use to derive test cases. Right? Okay, you look at the program and you say, I want to cover this branch and this branch and this branch and this branch, and this is actually structural testing, and that's what you can do. Okay. Or you go to the other side and say, the program should actually compute or sort a given set, and so I use that information to derive test cases. Right? And this is functional testing. Okay. Now, he's sort of very fan of function, not structural. So he says, okay, if I have to test the software, come on, take the specification, read the specification, use the specification to derive test cases. Right? Okay. And what about the code? Don't you use structural code testing? So, the approach is correct. You get to the specification and you understand what the specifications say and you derive test cases from the specification. And you do that because the specification gets much more information than the code. Gets more information than the code, and they actually give you also a sort of easier way to work conceptually with the specification. So if I give you the Java code and ask you, can you cover a given branch? Let's say it's not easy, it's a euphemism actually, it's very difficult. If I give you a specification that says this Java code should actually sort the input set according to criteria which is either descending or ascending depending on what it says, I'm sure you can start thinking, I get a sorted set, see if it works, I get a not sorted set, see if it works, I get an empty set, I get a set that is descending, or you can do many combinations. So it's obviously easier to read the specification and decide what cases you use to take the code, and to read the code and decide what cases to use the code. But people do actually, in companies, start from the specifications, derive the test cases, run the test cases, measure the code, actually use the code to work.
If you don't cover some range there, you can look at the code and understand the part of the specification you don't cover.
Oh, that's an interesting point. So he has a very nice indirect measure. He says, I want to know whether I cover the specification. And I test the specification, get the code, get the test, run the test on the code, and look at the code to see whether I cover the specification. Wow.
Right. There's no guarantee that those sources are correct, so...
Okay, he is more on the theory point of view. Since I know that either the specification and the code may be different, may be wrong. Even if I use the specification, I get the test cases, maybe still miss something because the specification is incomplete. Right? Yes. That's one better point, which is the specification may be incomplete. Wrong is at the back word, incomplete. And so if you take the specification and the specification doesn't say something, then the code, then you don't get enough testing. This is more likely the case. Okay? Yeah. Why? The code should implement something that is not written in the specifications.
Just because the coding is not mechanical process.
Exactly. So something that I really want you to understand, and I hope you understand well. When you talk about coding, no matter how detailed are the specifications, it's not a matter of writing good or bad specifications. Coding is not translating specification to source code, to programming language. It is a complex design process, which implies a lot of design decisions that may actually imply that the piece of code that is actually built does not reflect the specification structure. Okay. My favorite example is of the sorting system. If I give you a goal of writing a sorting routine, which algorithm do we use? Merge sort.
It depends, of course.
Okay, he's always okay. Which one? Your favorite?
Who sort, merge sort?
Quick sort, merge sort.
And so on. Heap sort.
Heap sort. Either of them or both of them or three of them?
Sorry?
You're suggesting you implement one of them or all of them?
Maybe all of them and compare after that which is better for particular task.
Okay, he's approaching the solution actually. I was hoping you are a bit more, I'd say, trained in programming because you started fairly strongly in the I'm asking another question which is out of the range of the course, which is I give you 10 elements to solve. Which algorithm would you use? Exception.
No. What elements you wish to get? Because there are particular source, for example, from STL elements, you should to get 20%, first 20% of elements with some criteria. So you have to sort all the range. So it depends on what elements should you want to get from the output.
Exactly. Well, almost exactly. So the point is, if you have to sort 10 elements, don't do quicksort. Come on. Quicksort. What is needed? Quicksort is better than insertion. Do you agree?
No.
No, exactly. It's not better than insertion. It's asymptotically better.
Asymptotically.
Well, okay. Let us say. So, when you say that one algorithm is n log n and the other one is n squared, you are suggesting that in the average, or in the worst case, depends, whether it's worst case complexity or average case complexity, there is one point on your x-axis after which is going to be better. Quicksort is not doing better than insertion for 10 elements. In any case, because or merge sort is not doing better than insertion for 10 elements. Do you understand this? Because the amount of preparation for quicksort and the amount of overhead for calling the code server, it's huge. So it works much better for 1,000 elements probably, but not for 10 or 50. So if you are a smart programmer, you would use insertion for small elements, you would use quicksort for mid-range elements. There are places where quicksort is really bad. Or merge sort that is really bad. If you still remember something, you have an algorithm course, I'm sure. Okay? So you probably remember that these algorithms are called in-memory sorting.
Yeah, of course.
If you have 1 million elements to sort, don't use quicksort, please. Because if elements are not, that's where you were going probably. If elements do not stay in memory,
which is why I suggested a heap sort.
Heap sort, exactly. That's a great suggestion. But not for 10 elements, not for 1,000 elements in memory. You get heap sort if you get to have to handle the disk space. And then you know that there are algorithms that are better if you actually have the set which is, well, let's say, when the set is almost all sorted, except like the last 10%, then you get to the worst case or the best case of different algorithms. And you know, I must confess that I spent a lot of my study in algorithm, but you know, depending on how the initial set is, you may get an algorithm which is usually bad, but much better for that specific case. And that's the case, for example, of a huge set where you add elements at the end every day and then you sort. So if I, for example, decide that I have a huge file of all the exams that I did so far. So let's get this example. You know, I want to get an average of the performance of my students forever. No, it's completely crazy. But okay, so I record all the name of the students and all the results of the exams. Okay, and then you know every day or every section, every 6 months, I add the results of the exams of you, for example, to my file, and then I resort them. Okay. Then I have most of the set sorted and only a small part not sorted. And if you go back to your algorithm book, you will notice that there are, this is a worst case of quicksort, for example, and it's the best case for other algorithms. Well, anyway, so to make it short, if you are a smart programmer and I tell you, can you actually build a library for sorting, you will not actually start and say, yeah, it says that I have to produce the sorted elements, so I apply sorting. No. You have 4, 5, 6 different algorithms implemented in the same library to build the different cases that do not show up in this specification. That's what is actually incomplete specification. And not wrong, actually. The specification is correct, the implementation is correct. It's simply that the design decision taken between the specification and the implementation are big. And sometimes you also forget the specification. So what you do usually is you start from requirements, you get the test cases, you measure coverage, and then you go back to and you look from the coverage and you understand whether there is something which is not covered. Now, I hope your comment convinced you that you may actually have huge amount of code which is not covered because of design decisions. Okay? But there may be code covered because it cannot be covered. Okay? So let's go back to this for a moment. So back to the question, even if, it is relevant to use some coverage, but now it is also relevant to know which coverage. And it's not just a tricky thing to say, because it's not that I try to generate fake set test cases that only match this one and not this one. This is a demonstration. I try to understand whether statement coverage is a good measure for what my goal is, which is understanding whether the code is covered well or not. Right? Now, let me go for a moment to this problem, which is the feasibility problem, and then okay. And then I did actually prepare my set of slides, and always when I teach, I change the order of the set of slides. It's something that I can't really follow the set. Okay, so in feasibility, I gave you one big example, which is requirements, design decisions, code cover requirements may not cover all design decisions. And so I get my sorting, I get my 2,000 test cases, I run the 2,000 test cases, and I get 75% of coverage. Because 25% is one case which is an important design decisions never showed up in the specification. So I was really smart in the specification. So I decided to get small sets, medium-sized sets, big sets, sets bigger than the size of the memory. But I still forgot sets which are 90% soft, which is where my library would trigger a different kind of library. So that's one part. There is a second part, which is no matter how good we are, we almost never reach 100% coverage. Okay. And that's not just a matter of design decisions. There are many things which are many statements which may not be executable. Okay, so let's get to statement coverage, or range coverage, as you like. So simple coverage right here. Now, the question is, why a statement should not be executable by code?
Well, if I don't expect something to execute that, I just provide some thorough exception here.
Exactly. So, yeah. So basically, what people would call in a small concept defensive programming or robust programming. You know, you actually, in many cases, if you are a smart programmer, that's why I was expecting. You know, this actually sort of contradicts the format performance because you look like an expert programmer, but in some cases, you know. Okay, if you are an expert programmer, you would actually write code for cases which should never happen. You know, this is called defensive programming, this is called robustness programming. You know, there are several different things. So there are many things, exceptions, things that you write. Just, you know, if this and this is true, then there must be an error somewhere. And people write this kind of code because, you know, really want to be sure that you don't fail. You know, nowadays, people would actually throw an exception and say, this is wrong. But, you know, also in old days, you know, all the Fortran programmers would do that. Okay, so it is obviously the case that, you know, and it's actually experienced many times. You know, if you actually get to, okay, you know, of course, if you write the code that actually computes the absolute value, you know, input x, if x is greater than 0, then x is not x, you can cover it. But if you get reasonable industrial size code, it's likely the case that you never get 100% coverage, even for stable. So there are two approaches you can get. One is, I know that about 10% of my code is not executable, so I accept up to 90% of it. Or let's look at the 10% of the code which has not been executed and see how to provide. Okay, which would you do? Approach A means I cover 90% of the code. I want you to read the 10% of the code and tell me why it's not covered. Approach B, I'm happy if I go over 90% or 85%. No choices really. A.
It's not feasible.
It's not feasible. Okay, so 90% of the companies will go to for B. So I told you at the beginning we were talking about engineering, trade-off between cost and analysis, because most companies will go for B. Most companies will do actually, they cover, they measure coverage, and they say, I'm happy if I go over the threshold. Full stop. You know, well, you don't know probably, but there are companies who actually do it. You can get switch companies. For example, if you work for avionics, for the aircraft industry, your software must be certified. One step of certification is to actually prove or expect your code, and it demonstrates, you know, that UI, each statement which has not been covered, has not been covered. So why is not executed? And that's actually approach A. For avionic, if people working in the avionic industry, they do actually do A. Okay? And Of course, you know, the reason is because of the reliability requirements is because, you know, cost there has less pressure, you know, because if you crash, it costs much more. It would be interesting to know at this place and get like a complete answer rather than a fake answer. Which criteria they actually use in avionics? So does anybody know which criterion is actually required for flying for software to fly? Okay, it's called MCDC. Do you know that criterion? Modified condition decision coverage. Okay, you don't know that. We have two choices. One is to actually go through that criterion, and the other one is to leave it as sort of something that you may want to investigate later, and we go for a new topic now. Okay, and I'm going for the second option because I'm getting late, so I want really to go through some more concrete things. Okay, so it's called modified condition decision coverage. You look over the web, you say type it and you get it, and it's actually interesting to understand what it is, why it works. But again, you know, we can do everything in a short course. Now, next. I have actually three sets of topics that I want to be covered. We'll probably cover only one between today and tomorrow morning. So I want you to choose which one. Okay. One is data flow analysis and testing, which gives you a nice combination of the two elements. Okay. The second one is functional testing, which gives you a functional model-based testing, which gives you criteria for getting from functional specification to model-based testing. So I have things like category partition, pairwise combination, final state machine-based testing. And the last one is program analysis. Okay. So I don't think we can cover the three of them. I didn't think it at the very beginning, and I actually get more just to be sure that I can choose whatever I want. We should start with one of them. Which one do you prefer?
Functional.
Is it functional? Other
Let's go to maybe.
Okay, both. Data flow? 1, 2, 3, 4, 5, 6, 1. Functional? Analysis? You know.
I'm in static analysis, of course.
Mostly dynamic, actually. Both static. I like dynamic more than static, but both of them. Voting didn't work because we get late. I think I get like 6 and 6, or 5 and 6 and 6, so I can't say that. Yes, let me do this. I go through analysis now because I think I can get it shorter, and then we go back to either functional or data flow. Okay? Okay, so what I like to go through is memory analysis, log set analysis, dynamic analysis, and relational algebra as analysis of software. Okay, how many of you know Purify? No. Log set analysis? No. Diaphragm? No. Alloy? Such. Okay, so. Now I was sort of worried about how much you know, how much you don't know. Okay, so let me go because we do have about 15 minutes, so we can do that. Couple of things, and maybe I will skip along since some. Okay, analysis. We go static and dynamic. Everybody knows the difference in static analysis. Static means I look at the code, analysis means I look at the code execution, all right? And you can analyze the code execution, all right? Now, why we do analysis? Okay, let me actually give you no. I don't give you anything because it takes more than I expected. Okay. Very quickly. Why we do analysis? We do analysis because many problems do occur already in the code. Okay? This is a very simple example. This is a piece of code that we use in the book, and it's actually sort of interesting, and says, well, this is of course not the full code, that's a small piece of the code. Do you know what CGI encoding is? CGI encoding. Common Gateway Interface. Okay. Common Gateway Interface, CGI for short, is an encoding used in web applications. So if you type your data on your window, actually it is encoded in a way that actually prevents non-ASCII characters to be transmitted. Okay? And the encoding is very simple. It basically says if you have a character, keep it. If you have a special character, it substitutes the special character by percent x and y, but x and y are hexadecimal digits. So let's say they call the hexadecimal as coding of special character is I don't know, 87. I don't know the ASCII table. So percent 87, codes that specific character in that case. And actually, that's an interesting little story which I don't have time to tell you, but we have this piece of code we used for examples in the books which we wrote, and basically it's a converter. It takes hexadecimal encoded strings and translates them into the original values. So if you have to translate this encoding, you read a percent and say, okay, now let's read the next 2 digits and translate them. Okay, this can be hexadecimal character or cannot. If they are not, it's an error. If they are, you transform them in the correct thing, and that's it. Okay, and the code is if the current character is percent, then call this hex value, which is in the table that converts this C, and actually EPTR is the pointer to the input string. If you've seen one C program once, you can read this. You don't have to be a professional C programmer. You have pointer to the string, you get the current character. If the current character is percent, you read the next character, and you convert it, and you save it, and you read the next by one character, and you convert it, and you save it, and then you can imagine the next step would be if digit high times 16 plus digit low is blah blah blah. So basically what you do, you convert these 2 digits into the corresponding character, and then you go loop again. Okay? It's wrong. Well, it's written down, so I can't ask you why, because if you can read English, you can get it. It's wrong because it's a classic C program. I remember I mentioned the thing, actually my students are working with C++, this leads to a memory leak. Actually, buffer overflow. Okay, it works in millions of cases, but if your input strings terminates with a percent, and one only digit, what that does is, this is actually in a loop. While end of string, you read the next character. Okay, so if the next character is this one, and this is the last character, they do not check whether the character is. So they advance EPTR by 2, and then you read something that is not supposed to be used. Okay? So it is wrong, no doubt. We actually had a failure at some point. It took us months to get the failure. And you know why? It takes months to get the failure because it's a very strange case, which is the case of the wrong string, so you can run it forever. You get this piece of code, you put it on your website, and you run it forever. And if the only way you use it is by actually reading the coded string, correctly coded string, you have everything coded this way. Okay? You get this program only if a nasty hacker understands how to feed into your program this terminated string. Which is exactly what happened with all these problems, like security problems, buffer overflows. They're not programs that are stupidly wrong. I mean, when you say buffer overflow, people, I usually look at the people and say, "Come, buffer overflow? What do you mean?" I mean, are you not a conscious programmer? No. It's not just a matter of being a conscious programmer going to do some reasonable testing. It's more like it's a matter of saying, yes, I did really everything well, and everything works well, all the classic cases. The problem is if someone learns how to actually feel in something that is not completely good. So this can escape testing just because this is a very special case. Even if you are a great tester, it doesn't escape testing. Why? It does escape testing because this is the case of a string of elements which is called that does not produce the original failure. So you read the string, set at the end, you go over the allocated memory, and so on. Only when later on you will use that string, you will actually probably experience some unexpected behavior. So we did test the program. We had the program, we did the program wrong. We did test the program. We actually used several criteria to select test cases. We produced very good coverage, and we ended up with not revealing the failure. Only at some point, with a very strange situation, we got this program failure. Okay? Now that's actually where you want to use memory analysis. Oh, I put purify in parentheses because there is a conceptual thing which is memory analysis, and what commercial thing is purify is distributed free of charge. It's a tool, it depends on which one. Purify is a tool that implements this kind of stuff. So if you look for memory analysis over the internet, you better look for Purify, actually. Right? Okay, now I'll tell you first what it happens and then how it works. The working is not that big. So what happens is you have your program, you put Purify on your runtime environment, you run the program, and you get this. Okay, actually, no, don't get this. This is actually the problem. Sorry, I get type 2. You get this. Okay? Now, it's not completely intuitive. It's the kind of thing that this one, once you learn how to read it, it's much simpler, but it takes time to learn how to read it. What actually is, it says, memory corruption detected. Summary of all memory leaks. Okay, so it actually helps you detecting the failure, the fault, even if the program does not fail. So the conceptual idea is very, very simple. If you have here a sentinel, okay, this is the end of the string. Okay, so this case is string, end of string. Okay. If you have a sentinel that says, that says this and this and these locations should not be accessed while scanning that string. And if you access them, they say bad. This is a memory leak. Then you discover it. Right? Now the problem is that the program does not discover it. And so Purify sits between the runtime execution support and the program execution, and that's exactly this thing. Right? Now I'll tell you how it does it, which is a very interesting thing, and then we go for it. Okay, it does it in this way. And that's exactly the spirit of analysis. It says, let's take one single memory location. Now, what is a memory location? There is a long paper that describes it, because actually the problem is a memory location can be a bit, can be byte, can be a word, can be blah blah. And this very boring paper actually but not too uninteresting. Actually, discusses the trade-off between overhead in analysis and precision in analysis. Okay, in our framework, it's a word. Okay, it's a memory location, and the memory location can have millions of states. Can include every possible combination of bits. Okay, but not millions, but several states. Okay. Now, actually, there are only 3 states that are important from this analysis, and that's exactly how good automatic analysis tools work. They abstract from many details and look only at the detail that actually is important for them. What they abstract from? They abstract from the value in the memory. Let's say, for the sake of this analysis, you don't care whether you write percent, or the coding of percent, or the coding of two, or the coding. You just care whether the memory is not allocated, or whether it is allocated, or whether it is initialized. Okay. Not allocated means the memory is not writable, is not bigger. Allocated but not initialized means it is writable but not readable. Allocated and initialized means readable and writable. Right? Now, what they do is, whenever you access the memory location, you associate to each memory location an information that says unallocated, allocated, initialized. And so all memory is initially not allocated. Whenever you allocate the memory, you go to the state allocate. If you deallocate the memory, you go back. If you actually initialize the memory, you go here. And if you deallocate the memory, you go back. And now each operation of that memory cell will be matched against the state. And what unified tells you is, oh, come on, this is what it tells you. It says, you got to this specific location of memory, which is supposed to be bounded for the array, and you were not supposed to write or to read from a non-allocated memory, and you did. Okay? So far it seems to be simple, and it is actually simple. There are a couple of problems that I want to actually point to you. One is, okay, how do we do that? So let's say this analysis is simple, it's very effective because it's really easy, but there is a very nice way of implementing it. So what they say, and this is what this huge boring paper is about, is to code to 3 states, how many bits you need? 2 bits. Right. So they say, I can actually do that bit by bit by associating to each single bit 2 bits of states. And then, of course, the overhead is about 300%. I can do that, but not word by word, by associated to each 16 or 32 bits words, 2 bits. And then the overhead is getting like 10% or 5%. And that's where actually they find a good trade-off. Of course, if you go bit by bit, you're much more accurate. If you go word by word, you're less accurate. But you actually associate only 2 bits to each memory location. And then you actually associate to each of the operations that access the memory the way the results of these 2 bits. And with an overhead of about 10-15%, which is maybe not acceptable on runtime, but it's definitely acceptable, for example, on testing time, and also sometimes at runtime, you get a printout that actually checks every time you access the memory what to do with it. Okay? Now, of course, there is a huge part, which I don't think I can deal with today, which is how do you actually implement that in an efficient way. And then there is the third part, which is still again is something that you do not, I don't have time to discuss, which is how do you deal with many programming tricks. For example, well, let's see how good you are as a programmer. You write a concurrent program, or you have a program, okay, and you want to, for example, now let's forget about it. We'll show it tomorrow with another kind of analysis, which is easier. I think, it's time to stop. You said, 10 to 1. Oh, sorry. Oh, we do have time then. Yeah. Sorry, I got the message that it was 10 to... So we do have time for a break also. Let me go a bit... sorry, I actually got... Okay, let me go for the next one. Okay, sorry, I got confused with the time. I thought it was actually time to stop. No, we have 1 hour left.
Yes.
Okay, so let's go for lots of analysis, maybe have another break and then continue to the end, okay? Okay, so, one simple analysis. Next kind of analysis, which I want to get more into this. Log set analysis, okay? Log set analysis, basically what you do is looking at a different class of faults, okay? So, what we learned from Purify or dynamic memory analysis is analysis can be effectively done automatically if you do at least 2 things. One is you focus on a specific property. Dynamic memory analysis does not tell you anything about concurrency, does not tell you anything about, but it tells you only about memory leaks and memory access problems. The second thing is if you actually can abstract from everything which is not interesting. So the other assumption is you can actually abstract from anything that are not interesting. These are the 2 main points where you actually can apply analysis. And it works pretty well because the class of properties is very clear and you can abstract a lot from that property. Oh, by the way, this is a great successful tool for C and C++ problems. Of course, it does not help much in Java programs. And the reason is simply that after more than 10 years of failures with memory analysis, so the story with, this is a sort of sub-story, it's not the whole story, but the story of one of the interesting stories about programming is that C came for many reasons, was really great, and C moved to C++ because of many other reasons. And people lived with all these memory problems, memory access problems for a long time. At some point, these problems were actually overcome. Rather than the people working with that, and so what they did was basically, let's stop here and let's try to find tools to solve that. And so people started thinking about tools, and this tool, Purify, was the most successful of a whole family of tools and works pretty well. And then people eventually got to the point that say, okay, look, why don't we write a new language where these problems go away just because we simplify the property? And actually, so this is a very nice example. Let me go back for a second. This is a very nice example of moving in this space, People were actually writing C and C++ programs. They were experiencing a lot of, they were actually moving on optimistic inaccuracy, which is testing, and they were experiencing a lot of problems with testing on a specific class of problems. Then at some point, they actually tried to find out a way of getting some pessimistic inaccuracy, and they moved to analysis. So they forgot many things, so it's not actually completely correct. But basically they say, okay, let's actually reveal. In fact, if you look at the output, it didn't show much about the Purify output, but many things that the Purify tells you are warnings that are not relevant. So the reason why it's not that easy to read and sort of be complicated is that it tells everything that happens, but not everything is relevant as a fault. And that's exactly what people need in a much larger scale. It's just a single project or a single program, which is a class of programs, is C and C++ programs. They say, can we get some tools in this, or some techniques in this area, on this axis, which actually would work better than testing? And that's exactly what Purify does. You actually combine optimistic or testing elements with analysis, optimistic with pessimistic, because that's actually dynamic analysis, and you do that in a way that actually helps a lot in solving the actual problem, okay? And it reduces the cost of solving the problem. So if you combine good testing practice with Purify, with dynamic analysis, you get more information about failures much quicker and much easier and at a much lower cost than if you actually try to make the program fail in the long run. Okay? And then people eventually move to Java, which is simplified properties. Okay? It's interesting because here you see really the path, and you see the path on the large scale. And one thing which is not easy to do and people don't usually do very carefully is you can do this path also, you can traverse this path also for single projects. Okay? So sometimes spending 15 minutes, half an hour thinking, can I do something better? It helps. Okay. Let me go back to the analysis now. Okay, and I'd like to tell you about lock set analysis, which is similar but also, but it tells you, that the same range of ideas would work really well also for a completely different class of problems. Like when you talk about analysis, the two classes, the two keys of the problem are memory management and concurrence. Okay, both cases you have problems that are difficult to reveal. Because in one case you need to get to the extreme cases and, the fault may not cause a failure directly. In the other case, you actually may test the system and see it working because you can't really control the speed of the system. So there are many problems that arise because of the sequence of operation, which are different from the way you actually work. And so what you do is you want to do some different things. And let me show you how dynamic lock set analysis works. Again, it's a combination of ideas, okay? First, we address one class of problems, databases. Okay, so again, analysis is effective because we do not solve all the problems, but we have one problem which is serious and we try to solve it. Second, we use a set of what's called lock set disciplines. So we assume we don't solve the problem in any possible case, but only in some cases. And that's actually, what is a lock set discipline? It's a set of rules that are used to prevent databases. Okay, so for example, one rule which is probably hopefully agreed among all of us is every variable shared between friends must be protected by a mutual exclusion lock. Okay? Of course you can achieve can solve the problem of race condition in other ways. For example, controlling the speed of the processes.
No, you cannot.
Who the hell will actually control the speed of the processes? Any ideas? Automotive, for example. The question is, of course, it looks funny, if you come from the school like me, where it is the school of the operating system that takes care of everything for you. So, if you come from the school that says we should not work on timing, but you should work on the logical correctness of the program, it doesn't make any sense to say, and no, that's actually very fast to don't matter. Actually, there are many cases where the overhead of locking and unlocking a memory region is too high and not necessary because you know in advance what the speed of the different processes is. It's dangerous in general, but it can actually be used everywhere. So this does not work everywhere. It works only if you use properly this locking discipline. There are several rules, but most of them are obvious, right? So it is the case. Now, the idea is very simple, as I show it on an example rather than reading all these stupid things, which is this one. You start, let's say you have a very simple situation, which is two threads, A and B. Okay. Now, where is the problem, where the problem comes from? The problem comes from the fact that in a real problem, in a real concurrent problem, you don't have only one single lock. You have tens, thousands of locks. And they actually are held, many of them are held in different situations. I don't know how familiar you are with concurrent programming to believe me on this. Okay, let's hope so. So, what the idea is you start with a set which is a set of all possible locks, which are statically related to variable. So, let's say I have only one shared variable which is x. And then you have two locks, 1 and 2. Of course, we have millions of locks and tens of variables, but that's another thing. Now, I actually start by computing the locks which are held at each step of the execution. So if thread A locks lock 1, it has lock 1 at this point. Now, whenever I access a variable, a shared variable, like x, which is a shared variable, what I do, I intersect the lock set held from the lock set, I intersect the lock held with the locks, right? So, initially, all possible locks are good. Now, only lock 1 is good, because only lock 1 is used when access is is called when accessing the variable x, right? Then I unlock, and so my lock set pair is empty, but this is the lock set. So this is the amount of locks that were called while accessing the variable so far, right? Now I have another thread B locks another lock. The lock set pair is lock 2. I access the same variable, I intersect the two locks, and I get an intersector. And then I unlock lock 2, and I have a warning. The warning says I have more than one thread, or I have several accesses to the variable, and the amount of locks consistently held all the times is 0. Okay. Interesting, this is correct. This execution does not make any wrong. Okay. So what it says is more than just the results of one single execution. It tells you, well, here I know exactly how many are, but it tells you after this execution, I can tell you that there is a subset of threads that can access the same variable with a mutually exclusive set of blocks. Which means if they run in parallel, they would actually create a problem. So, if you execute these actions in this sequence, you don't experience any failure. But if you actually execute thread A and thread B or concurrently, then you start lock, you access, you start lock, you access, you unlock, you unlock. You can do that, and you actually would experience a failure. Do you follow this? So, again, very simple analysis based on set intersection. And that's actually a trick why it works very well, because it's not a complicated thing that takes forever, takes 2 PhDs to just understand how it works. It's automatic. You can actually write the tool, run the tool, and forget about the tool. Okay? It works very well on a simple assumption. It doesn't tell you whether it is an error, it doesn't tell you whether there has been an error, it doesn't tell you why it is an error. It just tells you, look, in the formal execution, you actually went through a set of threads which had this bad property of actually being accessing the same set or same variables through different sets of blocks. Of course, the error may be simply that this should be lock 1 and lock 2. Or the error should be simply that there has a lock 1 which is actually forbidden in that specific case because of the condition of the if that regulated the code. You don't know why, but you simply say, if this is empty, there is a problem. Okay? And maybe not a fault, but then it's up to you to look at the code. Okay, now, last thing before the small break is this one. If you run lockset, or if you run that very naive way, then I lockset algorithm, you will get millions of warnings. Why? Well, you get millions of warnings. Why? For example, if you run a program if you write a professional program, so if you're not let's say, if you're a good programmer, you know that, let's say, you have this shared table. Okay, so you write a simple compiler, a simple whatever, and you have this shared table. Okay. What you want to do, you want to allocate the table, and then you want to run the program and use the table. Would you lock the table by allocating it or creating it? They don't. Anybody will lock it? Okay, the answer I start to put is no. But yeah, it is no. I mean, you don't lock the table because you know that in the initialization actually, you don't really need to actually lock the table because there's no one. It's like entering the room and saying, you don't want to come in this position, more than one person at a time. If I'm the only one in the room, how the heck can be any other one coming in? So actually, a good programmer should not waste time by locking the table while creating it, while initializing it. It will only start using locks once the table is created and running. Before the table is created, nobody accesses it. Okay. So, if you run offset, it will actually create millions of warnings which says, look, since you actually access the table without any lock, every access is a potential problem. Because you remember how it works? It works simply by intercepting the set of locks 10. Now, if anyone accesses the variable without holding a lock, it actually crashes the analysis. It says, oh, every access is a potential failure. And it's not true. So, a more realistic implementation takes care of these things. So there are policies that say you can do that. Because, you have two ways. One is forbid a programmer to do that, and it's never working. Because if you forbid the programmer to do that, you will exclude 99% of the problems from the analysis. Or, again, you attach a little information that says every element can be virgin, can be exclusive, can be shared, and it's shared modified. So, when you write on a data structure, then you go to an exclusive access. At this point, you can write and read and write through the first thread, and nothing happens. So if I'm the initializer, I can read and write and read and write, and nothing happens. At some point, someone creates a new thread, okay, and reads or writes. So if a new thread reads, you go to share, and you can read. Again, no problems. If I'm initializing and I'm the only one who writes and you can actually read, that's okay. The matter is that only with more than one thread accesses the memory in a reading mode. Now, if you now write, you go to share mode. And here you start lots of analysis. So it's, again, simple solution, but at this point you actually get a lot of good information on the okay? And now I think it's a good time for a coffee before getting to the next part of the. Very good.